When considering a damped rotor, it is very important to distinguish between the damping effects that can be associated with the stationary parts of the machine, usually referred to as non-rotating, damping, and those directly associated with the rotor or rotating damping. The former usually has a stabilizing effect that the designer can use to achieve the required stability in the whole working range of the machine. So, stabilizing effect. The latter, on the contrary, can reduce the amplitude of vibration in subcritical conditions. So, for rotating damping, we have to distinguish the subcritical range in which we have a reducing of amplitude of vibration, amplitude reduced. In the supercritical range, we have a destabilizing effect. Destabilizing effect. So designers must then be very careful when studying machines operating in the supercritical range, taking into account that all mechanisms increasing energy dissipation with the rotor can cause severe instability problems. So, increasing energy dissipation within the rotor can cause severe instability. These subjects are material damping, friction, and so on. The model that now we go to represent For example, this representation can be extended. This model can be extended to the damped system by adding to the right-hand side of a set of equations m x to point C plus the right hand have m epsilon omega squared cosinus of omega t plus fx of t, and the second m epsilon omega squared sinus of omega t plus f y of t. So in the right hand we have to add the generalized forces caused by damping. So here we have to add the damping force. Because the generalized coordinates chosen are the displacement in the x, y direction of point C, such forces are the components in the direction of the x and y axis of damping forces applied to the point mass in point C. So the force caused by viscous non-rotating damping is proportional to the speed of point C in a non-rotating reference frame. So we have to repeat this sentence. Because the generalized coordinates chosen are the displacements in the x and y directions of point C, such forces are the components in the direction of x and y axis of damping forces. Applied to the point mass, to the point mass 2, the point mass in point C, to point mass in point C. That is the geometrical, the elastic center of the shaft. The force caused by viscous non-rotating damping is proportional to the speed of point C. In a non-rotating reference frame, non-rotating reference frame, so we can write the vector F non-rotating Fn equal to Fn along x-axis and y-axis, proportional in the sense of Cn minus Cn x point C, y point C. And this is the velocity of point C in a non-rotating reference frame. And Cn is the non-rotating damping coefficient. The force caused by viscous rotating damping. Viscous rotating damping is proportional to the speed of point C as observed by a reference frame rotating with the same speed of the rotor. It follows that for the study of rotating damping, a rotating reference frame O, zeta, nu, and z must be introduced. And we have to design. So we have the non-rotating reference frame X, Y, and the rotating reference frame zeta, nu. And the angle is theta equal to omega t. The origin and z-axis of the rotating frame are the same as those of the fixed reference frame O, X, Y, Z. But axis zeta and nu rotate in the XY plane at the same speed of the rotor, the same speed of the rotor. When the rotational speed is constant. The angle between the two reference frames is simply given by omega t. If omega is equal to constant, the angle is simply theta equal to omega t. The force caused by rotating viscous damping can be expressed in the rotating reference frame as proportional to the speed of point C, expressed in the rotating frame, that is, Fr rotating zeta nu equal to F n zeta F n omega F r zeta F r nu, proportional in the sense of Cr to the velocity zeta point C, eta point C in the rotational frame, reference frame. But the coordinates zeta C and eta C in the rotating frame can be expressed as functions of the coordinates of the same point in the frame x, y, rotating to fixed between the two coordinates. There is a rotation, so zeta C and eta C is simply equal to the matrix R applied to the point xc, epsilon c, in which the rotation matrix is an object, an harmonical object with cosinus of omega t, sinus omega t minus sinus of omega t, cosinus of omega t. By differentiating equations, these equations, the velocity of the point C can be expressed as zeta point C, eta point C equal to the matrix not derived per x point C, epsilon point C, plus the derivation of matrix R applied to the vector not derived. Where the matrix R points is omega 4 minus sinus plus cosinus minus cosinus minus sinus of omega t. So from equation if R zeta nu equal to minus CR of zeta point C, eta point C, we obtain R x point c, y point c, plus matrix R point xc epsilon c. The same force can be expressed in the fixed reference frame simply by multiplying this equation by the rotation matrix R, the inverse, that is also the transposed, because the R matrix is orthogonal so rotational force in the x, y fixed reference frames is R transposed applied to the same force in the zeta nu x. And so minus CR per R matrix transposed per R matrix for x point C, y point C plus R matrix transposed per R point applied to xc, yc. But R transposed per R is the identity matrix. With simple computations, it follows that R matrix transposed per R point is equal to omega 0, 1, minus 1, 0. And so, the final rotating force in XY fixed reference frames is equal to minus CR per x point C, y point C, minus CR omega 0, 1, minus 1, 0 for xc, yc. So we have non-rotating force and rotating force. And we have to introduce both of them in the equation of motion, obtaining the result in matrix form. The mass matrix diagonal M0, 0M applied to x2 point C, y2 point C, plus a matrix containing damping coefficient, non-rotating coefficient and rotating coefficient in the diagonal position, so Cn plus Cr 0, 0 Cn plus Cr for x point C, y point C, plus, and this is an important, very important result, a unique matrix constituted by the diagonal usual stiffness matrix plus a new contribute proportional to omega skew symmetric 0, 0 CR minus CR. This is a unique matrix. This is skew symmetric, antisymmetric, skew symmetric, XC, YC. This is the left hand of the two equations composed in a matrix form. The right hand is equal to the unbalanced contribute m epsilon omega squared cosinus of omega t m epsilon omega squared sinus omega t, and the presence of external forces fx and fy. So this is, in a very compact way, the introduction of rotating and non-rotating damping to the original undamped system of rotor Jeffcot.